All right, we're going to start this acceleration due to gravity lesson with a little discussion here of what falls faster, heavy objects or light ones. So I want you to imagine you've got, I don't know, a heavy object in one hand, maybe like a hammer is what's often used, or a light object in the other, like a piece of paper or a feather or something like that. And the question is, which one falls faster? Well, if you can ignore air resistance, they're both going to fall at the same rate. If I was to drop actually a hammer and a feather here, well, in our classroom, let's say, because of the air, you know the feather's going to kind of float down, so the hammer's going to hit the ground first. But if you had like something thin, like, I don't know, like a pen, and then in the other hand a brick that was much heavier, and you drop those two objects, they're probably going to hit the ground at the same time because the air resistance doesn't affect it as much. So for a little bit of a history here, here's the question. Here's a hammer and a feather. Aristotle just kind of note at the bottom here the dates. We're talking, 2,300 or 400 or something years ago. A long time ago, Aristotle thought heavy objects fell faster than light ones. And normally I would demo this, and if you're in class with me when we do this, you might still get a demo. But Galileo came along, again, a long time later, 1500 or more like 1800 maybe years ago, or 1800 years later. Galileo kind of had this breakthrough idea that heavy and light objects fall at the same rate. The only reason we may not see that is, again, because of air resistance. Okay, so here's some great little videos for you to watch. The first one's really short. It's a terrible footage, but it's actually on the moon. They did this experiment on the moon with a hammer and a feather. It's grainy footage. It's kind of terrible, but the second video here, Brian Cox, it's much longer, but it's a great sort of high def view of this hammer and feather. I think they actually use a bowling ball and feathers, but you can see in a vacuum chamber that they fall at the same rate. So it's worth your while. Check those out. But trust me when I say that heavy and light objects fall at the same rate as long as there is no air resistance, okay? So we're going to talk about free fall. Free fall is only the force of gravity acts. There's no air resistance. We're going to use all of our favorite kinematics equations, okay, all the big five equations, but we're going to use, instead of a random acceleration value, if we're dropping something, or if we throw something up in the air or something like that, the acceleration value that we use is going to be this 9.8 meters per second squared. That is the acceleration of all objects due to gravity here near the surface of the Earth. If I go to another planet, or even if you climb a mountain or something like that, this value can change a little bit, but if you go to another planet, or like the moon or something, it'll be quite different there. But on Earth, as long as we're on Earth, 9.8 meters per second squared. You will memorize it, but it's on your equation sheet. You don't have to memorize it. That acceleration due to gravity, sometimes you'll see it written as acceleration due to gravity is 9.8, or you'll see it as little g is 9.8. When we sub that value in, we're just going to sub it into our a acceleration variable, I guess, in our equations. Okay, so kind of whipping through this quick, I just wanted to show you an example because this is where the good stuff really happens. So this is Mr. Gaglardi throws a baseball straight up at 18 meters per second. So let's imagine it kind of, I don't know, starts here somewhere and it's going to go upwards like this. And we can say down here at the bottom, let's say this is position 1. Down here at the bottom, let's see if I can squeeze it in here, V1 is 18 meters per second. Okay, so I throw it upwards, it's going up this way. And the question, part A anyways, is this, how high does the ball go? So we're looking from position 1, let's see if I can get back on there. There we go. We're looking from position 1 to position 2 is the highest point. And up here, I know something about the speed. You kind of know this instinctively maybe. If you throw something up in the air, when the ball is sort of at the lowest point, it's going this 18 meters per second. As the ball rises, it's going to slow down. It's actually going to stop just for a moment up there. Then it's going to start to fall back down. Okay, so there's our second piece of information. We also just kind of finished discussing about how acceleration is 9.8 meters per second squared. That is down. This 18 meters per second over here was up. Kind of don't have a lot of room there. What we're looking for how high the ball goes, we are looking for d. Okay, so what we're actually going to solve for is displacement, but we're just looking for distance when they say how high does it go. So there's our three variables that we know and our one variable that we don't. We can go ahead, choose an equation. We want to find an equation that has those variables in it. And I'd say this one fits the bill nicely. We've got no time given or asked for, so we're finding the equation that has no time in it. Ooh, we're going to go ahead and sub in some numbers here. I should say this. I'm going to choose anyways, up as positive. Okay, so that V1, when we sub that in, it goes in as a positive. When I sub in my acceleration though, it's down. It's going to go in as negative. Okay, so I'm going to bring this 2 times 9.8 is 19.6. I'm going to bring that to the other side. So it's negative 19.6d. I'm going to bring it to the other side here. It's going to become positive. 18 squared is 324. We'll divide both sides by 19.6. And we're going to find out that this d is, it's 16.53 meters. Okay, so as a displacement, remember what we've just found is a displacement. This thing is in the positive direction, so it's up. But when they ask for it in the question, they just say, how high does the ball go? We'll just put it with no direction. We'll just say, again, for sig digs, 2 sig digs, we'll say it's about 17 meters. That's the max height. Okay, so how high does the ball go? There it is, max height, 17 meters approximately. The tips down at the bottom just remind you, don't forget, pick a positive direction, kind of like we did up at the top here. List your knowns and unknowns, then choose an equation and sub everything in and solve. For part B, let's go over here. How long does it take to return to my hand? It's the same, I guess the same initial conditions, except we're no longer stopping up here at the highest point. Now the ball is going to come back down. So it's going to go up this way, come back down. V1 is still 18 meters per second. Now V2 is still 0 up at the top. But remember, what I'm going for now is I'm going from this position here down to this position here. So when you use these equations, so like this equation over here or any of the other equations, when you use them, you're considering 2 points. So make sure you think about where's position 1 and where's position 2. In part A, we went from 1 at the lowest point to 2 at the very top. Okay, so then we can sub in those values that kind of correspond to that part of the journey. Here we're looking at a different journey. Okay, so V is still 0 at the top. I just don't care about that. I'm going from position 1 down here to position 2 also down here. Okay, so I'll just rewrite V1 over here. Still 18 meters per second up. Acceleration due to gravity, always 9.8 meters per second squared down. Okay, 9.8 down. We no longer know that V2 is 0. Remember, V2 is 0 up at the highest point up here, but that's not my V2 anymore. V2 would be down here. I don't know what it is, and you may have a good guess as to what it is, and we can talk about that in a sec, but I'm going to ignore that for one quick sec. What I am going to mention is what is the displacement. Okay, so think about it for one sec. Between position 1 and position 2, what's the displacement of the object? If it starts in my hand and it ends in my hand, the displacement is 0. Okay, so it starts and ends in the same spot. This thing it did move, but its displacement is 0. What we're looking for in this then is time. We can go ahead, sub in, pick an equation. So I like this guy. I sometimes call it the best friend equation because I feel like I use this one more than any other. I'm sticking with up being positive. Okay, so displacement is 0, V1 is 18, that's positive. But the acceleration, negative 9.8, because that acceleration is down. Okay, like we did last time, this 1/2 times 9.8 is negative 4.9. If I bring that to the other side, it's going to become positive 4.9. And that 18t is still there. We can actually divide both sides by t. We can cancel out one of the t's. Okay, so you don't need to rewrite it, but I'll rewrite it just so you can kind of see where we are. We cancel out one of those t's. Now I can divide both sides by 4.9. 4.9's cancel over here. time, let's see, that is, it's about 3.67, and again, to reduce that to 2 sig digs, it's about 3.7 seconds. That's how long it takes to come back to my hand. That's it for this question, but just one quick little bit of a point of discussion here, I guess. I mentioned over here that this V2 was unknown. If something returns to the same height where this let's say V1 is 18 at this height, if it returns to the same height, that V2 is actually going to be the same value, but it's going to be down instead of up. Okay, so as long as something returns to the same height, as long as there's no air resistance, which is going to be true for all of our questions in this course, if it comes back to the same height, then V2 is the same as V1, just in the opposite direction. If it does not come back to the same height, so if it starts here, but it ends somewhere down here, so it goes up this way and comes down this way, then V1 here and V2 here are not going to be the same thing. But if it comes back to the same height, then they will be. Just quickly, you can kind of fill these directions in. So just something to think about. If I say up is positive, I can actually tell you what the values of all these accelerations are. I can't tell you the values of the velocities, at least not all of them, but I can tell you the directions. So think about it for 1 sec. If you want to pause the video, pause it just quickly, fill in all the accelerations, fill in whatever velocities you can. And hopefully you've guessed this, that all of these accelerations are all 9.8 meters per second squared down. Over here, same thing. These are all the same. And sometimes these two are obvious, but sometimes it's this one up here that is not obvious. Sometimes people say, oh, at the highest point, it stops. So acceleration should be 0. Remember, if v is 0 and acceleration is 0 at the highest point, then this thing is just going to hover up in the air. We know that doesn't happen. The ball, if it gets to the highest point, it's always going to fall back down. I think we talked about this one in class briefly, but v would be 0 at the highest point. On the way up, I don't know the values. It's going to be constantly changing, but something I can say is v is positive. So as this thing is going up this way, v is positive. On the way down, over here, v would be negative. Again, I don't know those numbers. Those numbers are going to be changing. So slowing down on the way up and speeding up on the way down. But I can say that v is positive on the way up and v is negative on the way down, as long as I'm saying up is positive. Nice, that's it.